universe is a constant exchange of energy, an infinite cycle of creation and destruction. Celestials use energy gathered from host planets to create suns, generating gravity, heat, and light for new galaxies to form. Without us, our universe will fall into darkness.
Imagine the universe, where every star, galaxies, and planets formed from a single, extraordinary event. It all started with a huge explosion, known as the Big Bang 38 billion years ago, where this universe, and probably countless other number of universes, it was the explosion that started everything. But how can we understand the origins of this universe? Here scientists formulate two major theories that shape our understanding of reality: the general theory of relativity and quantum mechanics.
100th anniversary of Einstein's general theory of relativity. So a little demonstration here at home to explain the essential ideas. So Einstein wants to know how the force of gravity works, how the sun communicates the pull of gravity across empty space to the Earth. Here's the idea he comes up with. He says that the fabric of space is nice and flat if there's nothing there, no stars, no planets, which would mean that if an object rolls through that environment, say this is a comet or a planet, it will go in a nice straight line trajectory. But the key thing is Einstein says that if we have a heavy, massive object like the sun, Einstein says that the sun, merely by being within the fabric of space, causes the fabric to curve, to warp. And then other objects, like the planets, the Earth, Mars, and so forth, he says, they go into orbit because they're rolling along the curved environment that the sun creates. This, according to Einstein, is how gravity is communicated from the sun to the Earth, to Mars, to the other planets. This is how gravity works.
General relativity. It was developed by Albert Einstein in 1915. Gives us a new view of gravity. He said that massa, an energy warps space and time, like a ball placed on a rubber cloth. The greater the mass of an object, the greater the curvature it causes. This theory brilliantly explains large-scale phenomena like planets, stars, and galaxies. But this theory faces a problem when we try to use it to explain the universe on a very small scale, which is the world of particles, subatomic or quantum.
I love you, Cassie.
Go separate. Go separate.
Oh no.
You would enter a reality where all concepts of time and space, and irrelevant, time and space become irrelevant. For all eternity. Everything that you know and love. love. Gone forever.
As you guys can see, how Ant-Man shrinks so small, up to be as big as a particle. Atoms themselves are the smallest particles that make up the universe, including humans. On the quantum scale, the laws of classical physics no longer apply. Particles can be in several places at once. Behaves more like a wave than a solid. The quantum world is full of uncertainty, probability, and randomness. Einstein once even said that the quantum world is so creepy, where all the particles are bonded and connected, even though it is very far apart. Einstein once even said, God does not play dice with the universe, he wants to reveal that everything is orderly and cannot be uncertain. Because physics is a mathematical calculation that is certain. However, Einstein was mistaken that the quantum world is random and uncertain. 90% of all visible material is empty, and that matter appears to be a wave. And then waves actually look like matter. Quantum reality literally makes scientists and physicists are confused.
Have either of you guys ever studied quantum physics?
Only to make conversation.
All right, so 5 years ago, right before Thanos, I was in a place called the quantum realm. And the quantum realm is like its own microscopic universe. To get in there, you have to be incredibly small. Hope, she's my she was my. She was supposed to pull me out, and then Thanos happened, and I got stuck in there.
I'm sorry, that must have been a very long 5 years.
Yeah, but that's just it. It wasn't. For me, it was 5 hours. See, the rules of the quantum realm aren't like they are up here. Everything is unpredictable. Is that anybody's sandwich? I'm starving.
Scott, what are you talking about?
So, what I'm saying is, time works differently in the quantum realm. The only problem is right now, we don't have a way to navigate it. But what if we did? I can't stop thinking about it. What if we could somehow control the chaos and we could navigate it? What if there was a way that we could enter the quantum realm at a certain point in time, but then exit the quantum realm at another point in time? Like before Thanos.
Wait, are you talking about a time machine?
No, of course not. No, not a time machine. This is more like, yeah, like a time machine. I know, it's crazy. It's crazy. But I can't stop thinking about it. There's gotta be...
As you guys can see, that even time within the quantum world, walk faster. 5 hours in the quantum world is equivalent to 5 years in the microscopic world. Even though quantum mechanics is currently under research. However, with the facts of the previous discovery regarding a very complicated quantum, and this strange poses a serious problem to the reality of life. How could a quantum particle, as these little things that make up nature, including the human body, looks like an illusion? Because it has no random certainty, and the absurd beyond space and time, beyond the limits of the human dimension. To understand more about quantum, you can read the article or journals that discuss quantum. Quantum research. This then gave birth to an interpretation of double reality, or parallel worlds and multiple universes, which is commonly referred to as the multiverse. It all started with a thought experiment that a physicist named Erwin Schrödinger, known as the Schrödinger-Scott experiment. Of the results of those experiments, he concluded that the state of superposition that occurs in humans, resulting in reality separating into two at the same time, as the cat is seen alive and dead at the same time. Before we open the box, to determine if the cat is dead or alive,
This was the invention of Hugh Everett III, who was a graduate student at Princeton in the 1950s. And he said, basically, look, you don't need all these extra rules about looking at things. Just listen to what the Schrödinger equation is telling you. It's telling you that you have a wave function, that you become entangled, and that the different versions of you no longer talk to each other. So just accept it. It's just, he did therapy more than anything else. You know, he said, like, it's okay. You know, you don't need all these extra rules. All you need to do is believe the Schrödinger equation. The cost is there's a whole bunch of extra worlds out there.
As already explained, that the Schrödinger experiment results in many realities, or the world. That led a physicist, named Hugh Everett, to spark his discovery, the controversial. There were many world interpretations in 1957. This interpretation proposes the existence of a parallel reality without the need for an external observer. In other words, reality is divided into many. There are so many universes, and also the world here. And there's even another version of ourselves, in different realities, or universes. This has led to a philosophical debate about the meaning of reality, and the existence of life.
You ever had that dream where you're falling as if you've been pushed off a tall building? That was probably me. The Darkhold exacts a heavy tone. Okay. All the more reason to give it a rest and let me have it. Here's the deal. I'll let you use the Darkhold if you give me your Christine. Yeah, I don't think she's gonna go for that. No? Didn't think so.
As you guys witnessed, how the Doctorate of Strength fights itself from another world. This kind of thing is not just a movie, but based on reality, from the research results and discoveries in science. Quantum mechanics is producing an increasingly complicated and complex reality, as explained in the clouds, that Einstein's general relativity explain natural phenomena and phenomena on a microscopic scale, by centering on the gravitational force affecting space, time, to regulate the circulation of the planet, stars and other celestial bodies. However, gets muddled when it comes to explaining symptoms and microscopic natural phenomena in the quantum world. When trying to apply gravity to the quantum world, the physicists found that the results of their calculations become inconsistent, often produce answers that don't make sense, like the infinity result or infinity. This shows that there are flaws in the understanding of gravity on the quantum scale, and the physicists needed to find a way to unify these two theories.
Imagine I have a beautiful tree that's filled with oranges. And I ask myself, what is the orange made of? How do I answer that question? Well, I want to look deeply inside the orange, so I magnify it. And I magnify it again, and if I keep on doing it, deep inside, sooner or later I begin to see molecules come into view. But molecules are not the end of the story, because the molecules, I can enlarge them. And if I make them big enough deep inside, I begin to see atoms. Atoms are not the end of the story too, because we have electrons zooming around the nucleus. Deep inside, mostly empty space in the atom, but deep inside, we see the nucleus. So if I grab that and magnify it, I see that the nucleus is itself made of particles, neutrons and protons. And if I grab one of the neutrons and magnify it, I find yet further particles, little tiny quarks inside. Now that is where the conventional ideas stop. String theory comes along and suggests that inside these particles there is something else. So if I take a little quark and I magnify it, conventional idea says there's nothing inside, but string theory says I'll find a little tiny filament, a little filament of energy, a little string-like filament. And just like the string on a violin, I pluck it and it vibrates, creates a little musical note that I can hear. The little strings in string theory, when they vibrate, they don't produce musical notes, they produce the particles themselves. So a quark is nothing but a string vibrating in one pattern. An electron is nothing but a string vibrating in a different pattern. A neutrino, nothing but a string vibrating in a different pattern still. So if I take all of this back together, I have my ordinary orange, and if these ideas are right, they are speculative, but if they are right, deep inside the orange or any other piece of matter is nothing but a dancing, vibrating cosmic symphony of strings. That's the basic idea of string theory.
String theory. String theory is the development of quantum thinking. Rather than viewing particles as tiny dots that has no dimension, string theory says that there actually is a tiny, one-dimensional string vibrating. Different vibes produce different particles, like a different nadai than a violin string. String theory first appeared in the late 1960s. The work of a physicist named Gabriel Venice. In the beginning, string theory was developed to describe particles that interact through the strong nuclear force. This string is a potential bridge between general relativity and quantum mechanics. When the string vibrates with a certain pattern, it could produce particles that carry gravity. It's called a graviton. This means string theory can unify gravity with and quantum symptoms. In string theory, Coke is no longer considered as tiny dot particles with no dimensions, but as vibrations or certain models of one-dimensional strings, which is very small. Coke is the notation or vibration pattern of this string. And each of these vibration patterns produces a different particle, including strong electrons and other particles that we're familiar with in quantum physics. Each string vibrates in different ways, and each vibration pattern. This results in different physical properties. Vibration of this string determines whether the particle is electrons or other particles. For example, if a string vibrates at a certain frequency, it can appear as a quark up. On another frequency, string can produce a bottom quark. Each vibration variation determines the characteristics of the particles, including massa, charge, and spin, that assign different roles in the formation of matter. Protons and neutrons, which is a component of atomic nuclei, formed from different combinations of quarks. Proton consists of 2 quarks up and 1 quark down. Neutron consists of 2 lower quarks and 1 quark above. In stream quark theory, this quark is the vibration mode of the string that binds to each other through a force carrier particle called first Grun that worked through the strong nuclear force allow this core to pull each other, thus forming a proton and neutrons. String theory requires additional dimensions outside of the three-dimensional space that we know. These extra-dimensional dimensions provide additional space for the string to vibrate in a variety of ways that allow the formation of particles different. In string theory, universe has up to 10 dimensions of space, with most of these dimensions being very small and rolled, so that we can't see it. These extra dimensions plays an important role in allowing a very diverse variety of string vibrations, which in the end explain the diversity of elementary particles that we find. String theory is a theory that states that all the forces of the universe can be explained thoroughly by combining general theory of relativity, or law of gravity, with quantum mechanics. Process of understanding the universe through this theory, by understanding phenomena in the real world, through phenomena in the quantum world or particles. This string theory produces this new idea known as quantum gravity. To get an idea how the quote works to form particles constituent of the universe, including the particles that make up our bodies, you can see the animation on this video. Then how does this string theory become a bridge between general relativity and quantum mechanics? As explained earlier, in simple terms, in quantum mechanics, particles, like electrons or photon, considered a point that has no dimensions. And this is causing problems when we're trying to understand the interaction of gravity on the quantum scale. When this concept of point particles was applied to general relativity, arises a calculation that results in infinity on certain values, which makes this theory inconsistent. String theory overcomes this by assuming particles as a vibrating one-dimensional string, because the string has a length, even though it's really small. When the strings interact, no dimensionless points produce infinity. In other words, strings have room to interact, thus avoiding problems that arise in quantum mechanics when gravity is involved. But the consequences are, string requires additional dimensions, up to 10 dimensions. This dimension allows the string to produce particles with certain energies and properties that can't exist in three-dimensional space, allows for the gravitational force that are naturally quantized in higher dimensions. In other words, general relativity and quantum mechanics can coexist without conflict in this extra-dimensional framework. This string theory has multiple versions, but we're just talking about it in outline. In the 1990s, physicists like Edward Within discovered that all versions of string theory are actually part of a larger theory known as the M theory.
M theory is an extension of string theory that was initially developed starting in the mid to late 1990s, when new mathematical techniques were developed to go beyond the mathematical methods that had been employed by string theorists up until that point. The math that string theorists had been using until the mid-1990s was based on an approximation scheme that gave us some insight into the nature of string theory, but it was somewhat coarse. The new methods were more precise, and with the new methods we learned new things. For instance, we learned that in addition to strings, in string theory, there are these other objects, two-dimensional extended objects called membranes, or three-dimensional objects, three branes, and so forth. So the M in M theory may stand for, it's still up in the air, but it may stand for membrane, the new ingredient that the refined mathematical techniques revealed.
As already explained, that the M theory deals not only with strings of one dimension, but also larger objects. It is called brands. This could have 2, 3, or even more dimensions. In string theory, we have 10 dimensions, but the M theory claims that the universe actually has 11 dimensions, which includes extra dimensions that are very small and hidden, as well as the dimensions of time and space that we know and perceive. In this Avatar movie scene can give us a picture and imagination about a different world, as well as his living creatures. Ideas and theories of modern physics that we've discussed in this video has opened the door to one of the most incredible concepts in modern physics, which is the multiverse, or many universes, because of the many dimensions, the universe. The universe, we may not be the only ones out there. There could be countless other universes, each with different laws of physics. These parallel worlds may have different dimensions. These different particles, even a very different reality, crossed my mind. Whether the tales and fictional stories of the ancients, as their reflection and understanding of the world, or other universes that live together with us. Because all of this looks like a fictional, it started to seem real. If the multiverse really exists, then our universe is just one of the many universes that may exist. Some universes may be similar to ours and a reflection of us, while others can be so different, so it's hard to imagine. Or one of these universes is the dimension in place where God dwells? If true, perhaps physics has detected the dimension of God's existence. Although everything is very complicated and complex, even hard to prove. But the potential is there. And it's hard to say none. Multiverse is not just a matter of the multitude of realities, but also a call to delve deeper into the meaning of life in the world that is full of possibilities and uncertainty. And one big question: will we go into another dimension of the universe after we die?